Hello class. Today we're going to be completing section 10.3 and we're also going to be reviewing for exam number 3. Sorry this camera's a little blurry here, but I'll be assigning 10.3 today, Wednesday, April 15. It'll be due on April 20. That would be next Monday. Also recognize our exam number 3 is coming up this Friday, April 17. So make sure that you're aware of that. That has to be done during the time that your class normally meets. So if you're in first period stats this Friday during that time, Central Standard Time, that's when you would be taking this test. It's not going to be available anytime like the videos for the particular lectures. The tests have to be taken during their normal classroom time. So I just want to remind you, make sure you schedule that in to your schedule this Friday, whether it's first period or second period, that you are ready to take a test. I will talk more about that test up and coming here as we continue throughout this day. We'll be spending some review time for that. Just a little background of where we've been. We've been comparing populations. What I mean by that, that's plural, populations, 2 of them. We've compared population means from 2 populations using large sample. Those formulas were so-so. They involved usually 2 standard deviations, 2 sample sizes, and a difference. You always remember a difference. But the formulas were not great, not horrible. We actually did the formulas. Then we compared means from 2 populations with small samples. Formulas were horrendous, if you remember. We did not expect you to use those formulas. We gave them to you as computer printouts. On the test, any problem that would have small samples from 2 populations would also be giving you a computer printout. The previous section, 10.2 previous, we've compared the means of 2 populations using paired samples. Those were great formulas because if you remember, we made a new column of differences, which meant we only had 1 new population. And hence those formulas were actually like the formulas we had back in chapter 9. They were very easy to work with. Today, we're going to do a comparison not of means, like we did in all of these, but we're looking at a comparison of proportions. The formulas are going to likely be real similar to the ones we had with means from large samples. You remember proportions are always only large samples. We do not have the capabilities to do the small samples for proportions. So again, these formulas will be similar to these up here, where we're expecting you to be able to use them. With all of these, I remind you again, we're looking at the difference between 2 populations. In this case today, the difference between 2 population proportions. I'm not sure that you need to copy all of this down. This is just kind of review. Here again, we're emphasizing the difference between 2 proportions, population 1 proportion minus population 2. We've had this before. The sampling distribution is this one. It's very good estimate of the population 1. It's an unbiased estimator of the population. That should be proportions. The standard deviation of that difference, this looks close to what we had with means. If you remember with means, you don't necessarily need to copy this down yet, but just watch. With means, this adjusted standard deviation, you remember, was S1 squared over N1 plus S2 squared over N2. This one is very similar to that, but it has proportions. Again, don't copy this down right now. This is also review. For it to be a large sample, you remember NP and NQ had to be greater than 5. Well, this would now have to be true for both samples. In all the problems we get in our book, they are going to be large enough. But if you were doing this kind of a test for a research project or something else, these would be conditions that you would have to be certain are satisfied. This one, I would like you to copy down. This is a confidence interval for a large sample. Large sample confidence interval for proportions. This is p hat. That should be a hat there. Came out of your textbook slide. And these would also be, in many cases, p hat and q hat. There is that priority list that we use for these PQs underneath the radical. We'll talk more about that later. You need to stop that. And again, if you wanted to write that maybe in just a little better form, it would have been p hat 1 minus p hat 2 plus or minus your z alpha divided by 2. That means we put half of alpha in each tail. Square root of PQ, usually that's 1 and 2, 1 and 1. And the second one is P2Q2 N2. These have the priorities of P and Q that we have in your notes as well. If you need to stop this to write that down, that's fine. Going back to this formula we use for all two population confidence intervals. That formula, okay? Hopefully you have a chance to have it copied down. We use it for all. The reason I emphasized for all has to do with this. I didn't write this Z here very well, but one of the issues that we have for our denominator with Z with two population proportions, there's two different types they use. For example, this one right here, that radical would go in this denominator. So what that means, I'm going to split this z-score is going to be P1 hat minus P2 hat, as we mentioned there. And we're going to go with this one. When our hypothesized difference is not set to 0. What I mean by that is that when this null is not set equal to 0, the alternative is not set equal to 0, then we use this denominator. So then I have this difference minus the hypothesized difference, because it's not going to be 0, divided by this one right here. P1, Q1 over N1 plus P2, Q2 over N2 with our priorities for that one. This is if this hypothesized difference is not set equal to 0. Now I'm going to do a different Z formula. For this denominator, I'm going to be putting this one in. So here's the other Z. This was the formula. If the hypothesized difference is not 0, not as common. This one is going to be over here now. So Z is equal to, it's going to be that same P1 hat minus P2 hat. This one is when it is equal to 0, so technically we have a 0 there. But now notice how I'm going to change this denominator. I'm going to be putting this one in instead. It is P hat general. Notice there's no 1 or 2 there. Q hat general. Again, notice no 1 or 2 there. 1 over n sub 1 plus 1 over n sub 2. This is where P hat general is both x's from the first sample and the second sample added together, divided by the sum of both samples. So this fraction goes in there. Q hat general is the complement of that. This is if the hypothesized difference does equal 0. This is the one most common because usually we do have zeros right there for our 1 or 2 tail. When it's 0, this is our z-score. We have to find P hat, and of course Q hat general is 1 minus P hat, the complement. That's a little confusing. Just go back a minute. This is the previous slide. This was our confidence interval. We always use that formula. When I do hypothesis testing, most of the time, I'm going to be using this formula for Z. Once in a while, if it's not 0, if it's not equal to 0 here, then I use this one. This one actually is, of course, part of your confidence interval. If you look at that radical right there, it's the same as this radical in the confidence interval. Again, if you need to copy that down, that's fine. I'll try to emphasize that as we go along here today. Sorry for the delay. Our first example. The American Journal of Public Health ran a test to determine if there was a difference in the proportion of employed people who got a routine yearly medical checkup versus the proportion of unemployed people who got a routine yearly medical checkup. If you were in class here, I would ask you, first of all, do you think there is a difference between the proportion? In other words, if I'm employed, am I more likely to get a routine yearly physical? Or if I'm unemployed, am I more likely to get a routine yearly physical? And I would ask you to raise your hands for who would vote for which, or if you think they're not different, you could say, I don't think there's enough difference there to be statistically significant. This type of test not only was run by the American Journal of Public Health, but it's run in a lot of countries around the world, especially the industrialized countries. And what they find is kind of shocking, all right? So these data points are not that unusual. Notice the American Journal of Public Health took a total sample of over 2,000. That is a huge, huge sample. And it's a random sample from across the country. The first part given is the 1,140 were the employed people out of this 22. Of these employed people, 642 had gotten a checkup. The other part of the overall group, 1,106 were unemployed. They found that 740 got the checkup. We want to test to see if there's a difference. Notice that's a two-way test. If there's a difference at an alpha level of 0.05. Okay, well, let's grind through this once. The first thing I got to do is I got to define what proportions each one stands for. Because the employed were the first sample, I'm going to let my P1 be the employed proportion. I know that's kind of small, but P1 is the employed proportion, which means P sub 2 will be the unemployed. Proportion. Well, one other thing I'm going to have to do here early on is I'm going to have to come up with P1 and P2, as well as P general and Q general. For example, I'm going to need P1 hat. That's the proportion of the sample from population 1. That's this 642 over 1140. It's X1 over N1. So this first sample, 642 out of 1140. That's going to give me, I'm going to round this off to 0.5632. Guess I didn't round it off that far. But that means Q1 hat would be its complement, 1 minus that. So Q1 hat is going to be 0.4368. Okay. I'm going to slide this up a little bit. So I have a little bit more room to work with. P hat 2 is the proportion from the second sample. The second sample, so that would be X sub 2 over N sub 2. The second sample had 740 over 1106, which turned out to be 0.6691. Its complement, Q hat 2, is going to be the complement of that, or 0.3309. And finally, I need P hat general. P hat general, you recall, was the sum of both x's, that's the 642 plus the 740, divided by the sum of both samples. That's why they call it P hat general. So it's going to be 642 plus 740 divided by both sample sizes, 1140 plus 1106. Well, you got to do that on your calculator, obviously, and what you get is 0.6153. It always should be somewhere between P1 hat and P2 hat. Not necessarily right in the middle, but this number should be somewhere between those two. Q hat then, general, is the complement of that. So that's going to be 0.3847. We need to do this initial work every time in advance, all right? So now here we go with our test. The null and the alternative. We're looking just to see if there's a difference, which means it's a two-tailed test. Remember the difference of the population, so that's P1 minus P2. Two-tailed would mean I set it equal to 0, and I set that difference unequal to 0. Step number 2. They gave us an alpha level of 0.05. I would have to show that N1, P1 is greater than 0. N2, P2 is greater than or equal to 0. And I would need to show that for its counterpart. This one is not going to be any issue because these proportions are towards the middle. They're not 0.999 or 0.001. And I got a huge couple of samples. So that's not an issue, which means I'm going to be using a Z statistic. They did not tell me that I had to use, I don't believe, no. They did not tell me which type of test that I had to use. So I'm going to do a critical value test or a rejection region. I'm going to be putting this 5% in both tails. Okay? It is very much like a 95% confidence interval. Again, it's been a while, but it would look like this. I take that 5% alpha and I break it up into two tails. So it's like a 95% confidence interval. We get 1.96 from our chart, negative. If I go over that line, so one rejection region is going to be Z is less than this negative 1.96. The other one is if it goes over that line, Z would be greater than a positive 1.96. Those are my two rejection regions. Step number 3. I need to calculate my Z. We're setting it equal to 0, the difference. So we use that second formula. What I'm referring to, again, is this formula right here, the one that we use the most often. You'll see me copying that one down now. So my Z is P1 hat minus P2 hat minus 0, all divided by square root of P hat general, Q hat general, 1 over N1 plus 1 over N2. Some substitutions here. P1 hat we found over here to be 0.5632 minus P2 hat is 0.6691 minus 0 divided by the square root. P hat general is 0.6153. Q hat general is 0.3847. 1 over the size of the first sample, 1140, plus 1 over the size of the second sample, 1106. So you would add the fractions together, take it times this factor times this one and take its square root. Divide that into the difference in the numerator. When you do that, you end up with a Z-score that turns out to be a negative 5.557. That, of course, is well over my line in the sand. Negative 5 is way out here someplace. It is in the rejection region. In fact, it's a long way there. Consequently, my conclusion, Z equal to a negative 5.557, is sufficient evidence to reject our null. Remember, our null said they were equal. We're rejecting that. And now conclude. Remember again, sufficient evidence goes with, now you're making a conclusion of this one, And you need to put it in context. Because the z was negative, it meant the second proportion, the unemployed one, is greater. Because when you take the difference, you had a negative up here. So I'm going to conclude the proportion of the unemployed is greater than the employed. And believe it or not, in industrialized worlds, that is the norm. That is kind of sad in terms of public health. That's why the American Journal of Public Health runs these kinds of tests. What they found is the people that are employed tend to believe they're too busy for a routine physical. The unemployed people probably have other reasons. Not, first of all, they're not too busy, but they're also maybe applying for jobs which require them to get their physical before they can get on the insurance company of the job. But the employed people, main reason is they just feel they're too busy to take time off. So the result of this test is actually pretty common, okay? They also wanted us to find a 95% confidence interval. Remember I said that formula is pretty standard every time. So I'm going to copy that formula down right down here. That confidence interval, it was P1 hat minus P2 hat. You have this in your notes already. Plus or minus your z-score, which will be that 1.96, times again P1 hat, P2 hat, excuse me, Q1 hat over N1 plus P2 hat, Q2 hat over N2. So putting those in there, we end up with this to be the difference here. I don't know if I have that. Let me see it. I do someplace. I do not. I would just have to substitute P1 hat in here, P2 hat in there, P1 hat, Q hat, 1 hat, and P2 hat, Q2 hat are these two numbers. When you do that, here's what you end up with your confidence interval to be. Turns out to be a negative 0.146 to a negative 0.066. What does that interval mean? Well, it was a 95% confidence interval. It means I am 95% sure that the second proportion of being the unemployed is greater than the first, because this is an entirely negative interval. If it went from a negative proportion to a positive, then I wouldn't be sure which one is greater. But because it's negative to negative, and I'm looking at the difference, the second one has to be greater. And I'm 95% sure of that. Not a big surprise, because that's what our conclusion was of our hypothesis test up here in step number 4. I'm going to go a little faster on this next example. I'll let you read that a moment. Real quickly, the first thing I would get would be P1 hat. It's 65 over 100, or 0.65, which means Q1 hat is the complement, 0.35. The second proportion, P2 hat, is 53 out of 100, 0.53. Q2 hat is the complement, 0.47. P hat general is 53 plus 65 over 100 plus 100. And if you do that, you end up with 0.59. Q hat is the complement, 0.41. The first proportion given was the mayonnaise. So I'm going to let P1 equal the proportion of the mayonnaise. Which means P2 is a proportion of soap. Okay, we're looking to see if we have greater loyalty of the mayonnaise customers. Notice the mayonnaise had 0.65, the soap 0.53. Is that enough of a difference that we have evidence that is statistically significant that would indicate a difference? That means because of the greater, we're looking at a single-tailed test. So step number one, the null. P1 minus P2 equal to 0. The alternative, P1 minus P2. P1 is mayonnaise. I'm looking to see if they're greater, so then that difference would be a positive difference or greater than 0. We have an alpha level 0.05. My percentages are right towards the middle, and I've got fairly large samples, but I'm going to state NP1 is greater than or equal to 5. NP2 is greater than 5. Therefore, I'm looking at a z-stat. I don't think it emphasizes which one, so I'm going to go with a p-value test this time, just to break it up. My z formula, because it's equal to 0, is again the one with the p hat, general hat. So that's going to be p1 hat minus p2 hat minus our hypothesized 0 divided by the square root of p hat general, that's this one, q hat general, that's the complement, times 1 over each sample size. Both samples were 100. So you would plug that in. I guess I can at least show it here this time. P1 hat is 0.65 minus 0.53 minus 0. Square root of P hat general is 0.59. Q hat is 0.41 times 1 over 100 plus 1 over 100. So this would be 2 over 100, or 0.02 times 0.41 times 0.59. Take the square root of that, divide it into that difference of 0.12. When you do that, you'll end up with a z-score. In this case, that happens to be 1.7. The p-value for that, it's a single-tailed test. So my p is going to be 1 times 0.5 minus the p-value for that. We haven't done that for a while, but 1.7 is 0.4554. 1.7, 0.4554. It's a single-tailed test, so I have one of those differences. And that turns out to be 0.04, I think, double check that z-score, 1.74554 did. So doing the subtraction, I'm going to have to do that here in a moment. I have 6 and I think 4.0446. Didn't write that down very well, but you get the idea. 0.0446. Because it's less than alpha, it's sufficient evidence to reject our null. So I'm going to state that now. P equal to 0.0446 is sufficient evidence to reject the null, and now conclude the mayonnaise customers have a greater proportion of loyalty. Again, a second example. All the same parts to our hypothesis test. We do have quite a bit of additional work here at the beginning with these proportions, but the formulas aren't as horrific as some of the small sample ones were. Okay. The next example I wanted to do, because when you're taking the test this coming Friday, it is really, really easy to get uncertain. Am I talking about the difference between two populations, or am I talking about a single population? Here's the easiest way to make that decision. Is this two population, or is it a single population? Whenever, listen carefully to this, whenever it's two populations, you have to have two samples. If you do not have two samples in the problem, it is not about a two population proportions. Here's an example now, again, of a single one. Radio Shack in home electronics, we did this one before, but it's a single proportion. It sells announces that it sells 21% of home computers. Is this claim supported if we have a sample of 120 out of 700 owners who buy from Radio Shack? Notice one sample, 120 out of 700. It doesn't say 120 out of 700 and then also 300 out of 800 or something. One sample that is screaming at you single population proportion. Okay, so make sure that you would recognize that going in. This is a sheet that I've put together to help you keep some formulas straight. I would strongly recommend pausing and copying these down. You can actually are going to be allowed a cheat sheet, 8.5 by 11.5, basically this size. And it would be, I think, to your advantage to have all of these formulas down. Here's where we were today. Okay, we were looking at two populations proportions. We only deal with large samples. Remember, our confidence interval was always that one right there. Our z-score could be any one of these two. Most often it's this one, and we use that in the previous two examples. This previous slide, we didn't finish it off because we did it in a couple lessons ago, was a single proportion. That was from a single population proportion. We would have used a much simpler adjusted standard deviation. We've done those before. But again, notice the formulas are easy because it's a single population. Single population. Last lesson, we did paired differences. We made a new column of differences that was a single population now. So our formulas became very similar to what we have right here and right here. These two are very much alike. The confidence intervals, very much alike for paired differences. It's why we like the paired difference ones for two populations. It's because our formulas worked out pretty well. Today, two population proportions, kind of messy. You recall a couple lessons ago, two population means, large samples, were kind of messy. Small samples were horrendous. We never asked you to do them. You will always get computer printouts if you have to do them. But these are formulas that you should have in your notes on your cheat sheet for the test on Friday. So if you haven't copied these all down, you should do so. Pause it, copy them down as needed. Next, this kind of chart, and this is kind of important here, so please try to catch this once because there's a lot in this kind of chart. These charts displaying statistical significance are becoming more and more commonplace in the business world. It's kind of important that you can read these charts and understand what they mean. We're looking at the differences in monthly gross sales, okay? The differences are in alphabetical order. So for example, this 800, it's the difference between A and G. Alphabetical order means it would be A minus G is the 800. This one is the difference between B and G. Alphabetical order, B comes first, so it would be B minus G is that one. C minus G is that one. D minus G is that one. Let's go D minus I would be this one. B minus H would be that one. Because that one's negative, B minus H, and it's negative, H had to be bigger. This one is positive. B minus G is positive, B has to be bigger. Does everybody understand what we mean by differences in alphabetical order? Now, here's the part that I really want you to pay close attention to. This asterisk indicates significance at 0.5%, if you will. That wouldn't have meant anything to you 2 chapters ago because you hadn't done any hypothesis testing. But this is screaming at us hypothesis testing at play here. Notice these stars right here, here, and here. They all indicate significance. What does that mean? What does that mean? It means this. If you had run a test between B minus F and saw if it was equal to 0 or if it was not equal to 0, two-tailed test, you would have had significant evidence. You would have had sufficient evidence to reject the null and conclude there was a difference. Specifically, F was bigger. If you had ran A minus F, notice there's no asterisk here. If you had ran A minus F and set that difference equal to 0 or not equal to 0, because there's no asterisk indicating significance right here, this one would have had insufficient evidence to reject the null. We would have continued to assume that the difference was 0. Basically, this chart is saying they performed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20 sets, 20 tests of hypothesis tests. And of those 20, 1, 2, 3, and 4 had sufficient evidence to indicate a difference. If it was negative, it meant the second one was larger. If the difference is positive here, D and G would have meant D is positive. It's becoming increasingly important that you can read charts like this, where they'll have some type of asterisk indicating significance. It's important that you understand that they basically had run all 20 of those tests, and they're showing you now a summary of which ones had significance in a relatively simple chart. There's a ton of information here, and that's why you're starting to see these more and more. They're starting to expect that you can read these charts and understand what we mean by significance at an alpha of 0.05, okay? A summary of that. Here's the same chart. I just put this in red. The asterisk, which is right here, 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 and here, indicates significance at alpha to be 0.05. This means the differences of B minus F, right here is B minus F, had the asterisk. D minus G, here's D and G, had the asterisk. A and I had the asterisk. And E and I had the asterisk. All four of those differences would have had sufficient evidence to reject the null, that they're equal, and they would now conclude the alternative that one of them is larger. This one was negative, so I would conclude F is larger. This one is positive, so I conclude D is larger. This one is positive, so I conclude A is larger. This one is negative, so I conclude I is larger. The others would have had insufficient evidence, and we would have had to continue to assume there's no difference. Again, I hope you appreciate the amount of statistical work that's been done just in that chart with those asterisks or lack of asterisks. Now we're going to start reviewing for our test coming up, okay? First thing I need to cover is details when I actually take the test on Friday. The test is going to be posted on Blackboard, but you're not going to have access to it till 8 a.m. Central Standard Time if you're in first period stats. If you're in second period stats, you won't have access till 9 a.m. Central Standard Time. I apologize, but we have to have all of you take it at the same time. I know that means if you're in the West Coast, you're taking that test at 7 a.m. or at 6 a.m. Okay, and I know that's kind of brutal. I apologize for that. I don't have much choice. Okay. I will also be emailing the entire class at their corresponding times, either at 8 or at 9, an email with an attachment of the same test. That's in case you're having trouble loading it from Blackboard. If you can't, for whatever reason, get Blackboard to work, I'm going to send you an email and you can open it up on the attachment on the email. Both sections will have a Dropbox that will be open for 90 minutes after their starting time. So that means if you're in first period stats, you got from 8 to 9:30. Second period stats, you got from 9 to 10:30 to do this test. Don't miss this now. You're going to be asked to provide blank sheets of paper when you come to take the test. You're going to write all your work on that blank piece of paper and your answers. You'll then take a picture, just like you do with your assignments. You're then going to put it in the corresponding Dropbox for the test, just like you do your assignments. I want to double emphasize, be sure it is really dark and bold print. Use a big, heavy, thick pencil if need be, or a dark pen. Make it very readable. It's one thing to have an assignment that's hard to read and you might lose points, but you don't want to lose points on your test because I can't read it. And keep in mind, I'm an old man, so I have a hard time reading to begin with. So make this really dark and bold. I'm warning you here ahead of time, okay? Make it very, very clear. Here's the breakdown of some tests. Chapter 8, which was on confidence intervals. There'll be 4 out of your 10 questions. Chapter 9 on hypothesis testing. That was all single populations. Single populations, there'll be 5 questions. Chapter 10, I call it specialty. but that's where we had two populations. Two populations might mean I look at the difference. It might mean that I do paired testing. So the two populations could be difference or paired testing. Okay, difference of two populations or paired testing. Only one question. Obviously 90% from chapters 8 and 9. All right, that's the crutch of understanding confidence intervals and understanding hypothesis testing. Chapter 10 is one small specialty off of chapter 9. But 8 and 9, quite frankly, are the two most important chapters in this entire course. So chapters 8 and 9, 90% of this exam. You will need to do 4 hypothesis tests. Of these 10, 4 of them you're going to have to write out the entire hypothesis test. That means steps 1, 2, 3, and 4, whatever else might be needed. Okay? Sometimes I'll ask you to do a critical value. Sometimes I'll ask you to do a p-value. If I don't specify, you could do your choice. Both the Z chart, that's of course this one, as well as your T chart, which I don't have a picture of here right now, they're going to be on the last 2 pages of your test. You will need to find one confidence interval. So out of chapter 8, one of these 4 questions, you got to find a confidence interval. The other 3 questions are going to be something about confidence intervals, a little bit more theoretical. You may have an 8.5 by 11 cheat paper. That's about big enough to be an open book test. You can go both sides of that 8.5 by 11. A lot of things you can write on there. If you want, you could even copy down a hypothesis test of some problem if you want to see all the steps numbered out. That's totally up to you what you put on there. Organizing this cheat sheet is probably the best way to study, actually. Some main concepts to refresh on. Confidence intervals. Some things that you should know. You should know how to interpret any confidence interval in context of the problem. What does it mean? Know what things affect the size of the interval. That means how big or wide is it, or how small or narrow is it? What things affect that? What ways do they affect it? If I raise the sample size, does that make it larger or smaller? If I raise the confidence level, does that make it larger or smaller? Those are things you need to know. Know the differences between Z and T distributions and know when you got to use each one. And obviously you're going to have to be able to use your calculator. Getting through a lot of those formulas, being able to plug them into your calculator is going to be crucial for you to get the correct Z on a hypothesis test or a correct T, or if you're looking at confidence intervals or you're looking at paired differences, you have to be able to get standard deviation and means. A lot of calculator skills that are demanded on this test. Some main concepts for hypothesis testing. We should understand what is a type 1 error, type 2 error in context of the problem. So refresh yourself. We haven't done a lot of work with those other than way back in 9.1, I believe. We should know how to run critical value tests as well as p-value tests. We did one of each today. We should know the logic behind the test. When do we reject and when do we not reject? What do we conclude or what do we assume when I have sufficient or insufficient evidence? We should know the difference between single-tailed and a two-tailed test. We should know the difference between a single population mean proportion, or single mean versus single proportion. That means single population mean, single population proportion. A comparison of two means, that would be two populations, a comparison of two proportions, and a paired difference testing. That's where I make that new column of differences and I find the mean and standard deviation of that new column. Here are some what I would consider important questions when considering what type of problem am I looking at. One of your biggest challenges on your test is you're going to get all of these types of confidence intervals and hypothesis testing scrambled through each other. You got to be able to read a problem and know what type am I looking at. Because if you know what type you're looking at, then it's pretty easy to go back to that formula if you know you're dealing in this type or this type or this type, it's pretty easy to go back to all these formulas and plug them in. Again, just a little suggestion. If you think you're in this type and you can't get all the details from the problem, that probably means I picked the wrong type of problem. Maybe I should have been some other place. An example, a real common mistake. People think they got 2 population means, so they start going with this formula, and they only have 1 sample. They say, well, where's my second sample? Well, the fact that they didn't give you a second sample probably tells you you should have been over here in a single population. That's, again, just a helpful hint, okay? But I would probably put these questions down on my cheat sheet. You can put them in any order you want. But one of the things I would first ask myself is this: is the problem asking me to find a confidence interval? Is it asking me to find a hypothesis test? Or is it asking me to find both? Or sometimes it might say, don't run the test, don't find the interval, just interpret the interval or interpret a test. But look at what the problem is asking you to do. Make sure you get that down first. And again, for that reason, if they're asking me to run a confidence interval, I'm looking at this formula. If they're asking me to run a hypothesis test, I'm looking at one of those 2 formulas. It determines what formula you're going to be using. Second question, is it a single or 2 population? Again, I want to remind you, for it to be 2 populations, you must have 2 samples. If you do not have 2 samples, it cannot be a 2 population problem. Is it asking you to find a mean or proportion? For example, back to here, single population mean means I have a standard deviation. Single population proportion means I have the PQ over N. Different formulas here. You need to recognize that early on in your problem. Is it a large or small sample? Large means, of course, I use Z. Small sample, I'm using T. But those are pretty important questions that you should know the answers to almost before you start the problem. Okay? That's all I have for our review. Test coming up this Friday. Make sure you schedule time into your schedule so that you are there for that 90-minute time slot. And you're ready to go, okay? Have a good rest of your day.